From now on, we will work mostly in the polynomial ring f bracket x, where the coefficient ring f is a field. So for example, we would work in r bracket x, where r is the field of real numbers, and say z7 bracket x, 7 being prime, but not in z9 bracket x, or not even z bracket x. The main reason for this is that in f bracket x, we can perform long division of polynomials, and that leads to the division algorithm in f bracket x, which, as we've seen in the previous lesson, is a very powerful tool. Now, speaking of the division algorithm, for the next several lessons, there'll be an underlying theme which we'll call big picture stuff, which states the following. The ring of integers z and the polynomial ring f bracket x, where f is a field, have many structural similarities. For example, both rings have the division algorithm. And here are the division algorithms in both rings, z and f bracket x. Notice the similarities, in particular how the remainder must be strictly less than the divisor in both cases. The focus of today's lesson will be on factoring of polynomials. And to get us started, let's take a look at the claims that are made by our friends. Elizabeth says that the polynomial x squared plus 1 is unfactorable. But Anita says, actually, it is factorable, and she shows us the factorization of x squared plus 1. So if you could pause the video and see if you agree or disagree with our friends. Let's start with Elizabeth's claim that x squared plus 1 is unfactorable. Now, this is true if we're in r bracket x. In other words, if we view these coefficients to be real numbers. However, if we are in z5 bracket x, then x squared plus 1 does factor as x plus 2 times x plus 3. And to verify that, let's multiply this out and see what we get. So we get x squared plus 3x plus 2x, so that's 5x, and then plus 2 times 3 is 6. But these coefficients are in z5, so 5 becomes 0, and 6 becomes 1, and in fact we do get x squared plus 1. So it is factorable in z5 bracket x. So the takeaway from these two examples is that we can't just say x squared plus 1 is unfactorable. What we need to say is x squared plus 1 is unfactorable in a particular polynomial ring, say r bracket x. Now, what about Anita's claim and her factorization? Well, the problem with this is that in a legitimate factorization, both factors must be less than x squared plus 1. And we're talking about polynomials here, so less in terms of its degree. However, in Anita's factorization, the factor 1/3 x squared plus 1/3 has degree 2, just like x squared plus 1. And so this is not a legitimate factorization because one of its factors is not less than x squared plus 1. Motivated by the examples we just saw, we will give definitions of factorable and unfactorable polynomials. So first, here's the setup. Let f of x be a polynomial whose coefficients come from a field and whose degree is greater than or equal to 1. So we don't even consider constant polynomials when we talk about factorable or unfactorable polynomials. Then we say that the polynomial f of x is factorable in the polynomial ring f bracket x if we can factor it, In other words, if we can write it as the product p of x times q of x, where the degree of p of x and the degree of q of x are both less than the degree of f of x. In other words, to have a legitimate factorization, both factors must be less than f of x. And otherwise, meaning if f of x is not factorable, then we say that it's unfactorable in f bracket x. And here's a remark, and this is part of the big picture stuff of the structural similarities between the integers and these polynomial rings, namely that factorable and unfactorable polynomials are analogous to composite and prime integers. Even with composites, when we factor, say, 15 as 3 times 5, notice how both factors 3 and 5 are less than the original integer 15. And so we have the similar kind of requirement for a legitimate factorization of polynomials. Now please pause the video and work on day 30 classwork, and afterwards we will review some of the questions and concepts. Let's begin by considering degree 1 polynomials. So these are linear polynomials, such as f of x equals 2x minus 7 in r bracket x, where r is the field of real numbers. Now this is an unfactorable polynomial, and in general we have the following theorem. Let f of x be a polynomial in the polynomial ring f bracket x. Then if the degree of f of x is 1, so if we have a linear polynomial, then f of x is unfactorable in capital F of x. Now, intuitively speaking, this theorem is true because degree 1 polynomials are too small, and therefore we cannot factor f of x into smaller factors. But for a complete proof of this theorem, please take a look at chapter 30 in the textbook. Next, let's consider polynomials of degree greater than or equal to 2. Now, this theorem has two parts, and here's the first part. If f of x has a root alpha, then f of x is factorable in the polynomial ring. Recall from the classwork that alpha is a root of f of x means f of alpha is 0. So when you substitute alpha in for x, we get the value of 0. Then by the factor theorem from the previous lesson, we know that x minus alpha is a factor of f of x. In other words, f of x has a factorization x minus alpha times another polynomial q of x. And then by the property of degrees, we know that the degree of f of x is the sum of the degrees of x minus alpha and q of x. And we will use this degree relationship to verify that the factorization of f of x is legitimate. And so let's start with degree of f of x. By our assumption, we know that this is greater than or equal to 2. And degree of x minus alpha is 1 because x minus alpha is a linear polynomial. And then 1 plus degree of q of x equals degree of f of x, and therefore degree of q of x must be less than degree of f of x. In fact, 1 less than the degree of f of x to be specific. And hence, the degree of x minus alpha and degree of q of x are both less than the degree of f of x, and therefore this factorization is legitimate, and hence f of x is factorable in f bracket x. Now, part A of this theorem deals with a case where f of x has a root. But what if f of x doesn't have a root? Well, that's part B, but we also need an extra condition. For part B, we must assume that the degree of f of x is either 2 or 3. And if that's the case, we have the following. If f of x has no root in the field f, then f of x is unfactorable in the polynomial ring. And it's important here that the degree of f of x is 2 or 3. We cannot use part B of this theorem if the degree is greater than 3, as we saw in problem 6 of today's classwork. And in the next slide, we will discuss the proof of part B of this theorem. And here is part B of the theorem. Let f of x be a polynomial whose degree is 2 or 3. And we claim that if f of x has no root in the field f, then it is unfactorable in the polynomial ring. We will give an outline of the proof, and for the complete proof, please take a look at chapter 30 in the textbook. Now, if we look at this theorem, it has no root, and f of x is unfactorable, lots of negative language. And as we typically do in those situations, let's prove the contrapositive, which is if f of x is factorable in the polynomial ring, then f of x has a root in the field f. And so we've identified the hypothesis and the conclusion, and those are the first step of the outline, assuming that f of x is factorable. And our very last step is to claim that f of x has a root. And so now let's fill in the intermediate steps of the outline. So since f of x is factorable, it has a legitimate factorization. In other words, f of x is equal to p of x times q of x, where the degree of both p of x and q of x are less than the degree of f of x. Now, using the property of the degree, since f of x is the product of p of x and q of x, we can say that the degree of f of x is the sum of the degrees of p of x and q of x. And here's where we use the fact that the degree of f of x is 2 or 3. We also know that the degree of p of x and degree of q of x are both less than the degree of f of x. So the only way this is possible, if the degree of f of x is 2, then we'd have 1 plus 1. If the degree of f of x is 3, we must have either 1 plus 2 or 2 plus 1. Again, given the restriction that these degrees are both less than the degree of f of x, those are the only possibilities. And therefore, we're guaranteed at least one of these, either the degree of p of x or degree of q of x. At least one of those must be 1. So we're going to assume that it's degree of p of x that's equal to 1. And the other case, if the degree of q of x is equal to 1, well, we can proceed similarly. So let's just assume, going ahead, that it's p of x whose degree is 1. And because p of x has degree 1, it is a linear polynomial of the form ax plus b, where the coefficient a is not equal to 0. And therefore, p of x has a root, namely alpha, which equals negative a inverse times b. And a inverse, or the multiplicative inverse of a, must exist because a is non-zero and because these coefficients are in a field. Once again, this is why it's critical that our coefficients come from a field. Now, as a concrete example of this root alpha, let's take a look at p of x equals 2x plus 7 over the reals. Then its root is negative 7/2, which we can think of as negative 2 inverse times 7. So it has the form negative a inverse times b. Then we claim that this same alpha happens to be a root of f of x, because if we plug alpha into f of x, we get f of alpha equals p of alpha times q of alpha, but alpha is the root of p of x, so that gives us 0 times whatever q of alpha is, the product is still 0. And therefore, f of x has a root alpha. And that's the end of our proof outline. And this is the end of our lesson, and I will see you next time.